10,
CLS is go for main engine start.
6, 5, 4, 3, 2, 1.
We built the most expensive scientific instrument in human history. We launched it into space 1 million miles from Earth, aimed it at the darkest corners of the cosmos, and waited. The James Webb Space Telescope cost $10 billion, took 30 years to build, and was designed for one central purpose: to show us things we had never seen before, things we assumed we already understood. And for a while, it delivered exactly what we expected. Stars, galaxies, nebulae, the beautiful, familiar furniture of a universe we thought we knew. But then the scientists pointed it at a planet. Not just any planet. A world bigger than anything in our solar system. A monster made of gas and storm and fury, 13 times the mass of Jupiter, drifting alone through the void without a star to orbit. A free-floating colossus sitting just 20 light-years from Earth, close enough that we have watched it for nearly 2 decades without understanding it. They pointed the telescope at it and turned on the instruments. And what came back broke the models. Not one model, not 2. Every single computer simulation, every atmospheric prediction, every assumption about how a planet this size should behave, all of it was wrong. The data showed something that the scientists were not prepared for, something that forced them to sit back from their screens and ask a question that has no comfortable answer. If we are this wrong about a world this close, what else are we wrong about? Here is why that question keeps physicists awake at night. We didn't just find one anomaly. We found 7 distinct atmospheric discoveries so unexpected, so layered, so deeply strange, that they are forcing a complete rewrite of how we think giant planets work. And not just the giant planets in distant star systems, the giant planets in our own backyard, possibly the planet that shields Earth from asteroid bombardment. Possibly the planet whose gravitational influence allowed life to exist on this rock at all. If we are wrong about Jupiter's cousins, we may be wrong about Jupiter. And if we are wrong about Jupiter, we may be wrong about why we are alive. But we are getting ahead of ourselves. Let's start with the discovery that started all of this. Let's start with the world that should not exist the way it does. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Okay, let's talk about Epsilon Indi Ab. That name sounds like a catalogue entry, and that is exactly what it is. Epsilon Indi is a star. It is a K-type star, slightly smaller and cooler than our Sun, sitting in the southern constellation Indus, approximately 12 light-years away from Earth. For context, 12 light-years is close. In the language of cosmic distances, it is practically next door. The nearest star to our Sun is about 4 light-years away. Epsilon Indi is 3 times farther than that, but in a galaxy that is 100,000 light-years wide, 12 light-years is a rounding error. Ab is the designation of the planet orbiting that star, and this planet is the first piece of evidence. Here is what the scientists expected to find when they pointed the James Webb Space Telescope at Epsilon Indi Ab for the second time in 2025. They expected to see a cold gas giant behaving like a cold gas giant should. The planet has a surface temperature of approximately 275 Kelvin. That is about 2 degrees Celsius, just barely above freezing. For comparison, our Jupiter sits at around 140 Kelvin, which is negative 133 degrees Celsius. So Epsilon Indi Ab is warmer than Jupiter, but it is still frigid by any human standard. Scientists believe this extra warmth was residual heat from the planet's formation, heat it is still slowly radiating away as it cools over billions of years. At that temperature, the chemistry should be predictable. The atmosphere should behave in a specific way. The models were clear about what would dominate the upper layers: ammonia. Ammonia gas and ammonia clouds, layered in visible bands the way our Jupiter is layered. Jupiter's famous stripes, those orange and white ribbons visible through a backyard telescope, are largely the product of ammonia chemistry. The models for a Jupiter-like planet at 275 Kelvin said the same thing would happen. Ammonia. Everywhere. Unmistakable. So they looked, and the ammonia was missing. Not absent entirely. There was ammonia, but not nearly enough. The signal was suppressed, weaker than it should have been by a factor the scientists could not explain away, as measurement error or instrument noise. This was not a faint discrepancy at the edge of detectability. This was a gaping hole in the data where there should have been a mountain. Think about what that means in practical terms. You are baking a chocolate cake. You know the recipe requires a full cup of cocoa powder. The smell of chocolate is the dominant feature of any chocolate cake. You bake it. You open the oven, and the kitchen smells like vanilla, not chocolate. Vanilla. You didn't put vanilla in, you have no idea where the vanilla is coming from. And the cocoa powder you used is nowhere in the scent profile. That is the level of wrongness we are talking about. The dominant chemical signature of the atmosphere was absent. Something else was there instead. Something that had swallowed the ammonia, buried it, hidden it from every instrument. The scientists looked at the data. They ran the numbers. They explored every alternative explanation they could construct. And they found the answer. And the answer was more unsettling than the missing ammonia. Water, ice, clouds. Let's pause here because the word clouds does not adequately convey what this discovery means. When you hear ice clouds, your brain probably generates a pleasant image. A cold winter sky, cirrus clouds, thin wispy structures high in the atmosphere that catch the light in delicate ways. What we are talking about on Epsilon Indi Ab is something categorically different. These are not decorative wisps. These are planetary fortifications. The water ice clouds on this super-Jupiter are thick, dense, patchy but massive. They are the kind of structures that don't just float in the atmosphere, they command it. They reorganize it from the top down. When the team led by Elizabeth Matthews at the Max Planck Institute for Astronomy analysed why the ammonia signal was suppressed, their conclusion was not that ammonia was absent. Their conclusion was that a thick, uneven layer of water ice cloud was sitting directly on top of the ammonia layer, blocking the signal like a planetary storm system blocking radar. Imagine you are trying to take an X-ray of a building from an airplane, but someone has parked an aircraft carrier above the building. The X-ray cannot penetrate the aircraft carrier. You see the aircraft carrier, you don't see the building. The ammonia is the building, the ice clouds are the aircraft carrier. Here is why this matters beyond the poetic imagery of a frozen giant planet. The computer models we use to understand gas giant atmospheres, the models we have built over decades of studying Jupiter and the hundreds of gas giants discovered around other stars, those models do not include clouds like these, not because the scientists were lazy, because including clouds in atmospheric models is extraordinarily complex, and the assumption up until now was that the simplified models were close enough to reality to be useful. Epsilon Indi Ab just proved that assumption was completely wrong. The real atmosphere of a cold Jupiter-like planet is not a simplified laboratory equation. It is a three-dimensional, dynamically shifting machine of ice and gas and chemistry that our best simulations cannot yet reproduce. Every prediction we have made about cold giant planets based on those simplified models has to be examined with new suspicion. Every single one. And here is the thing that should genuinely disturb you. We did not find this anomaly on a distant, exotic world in a strange star system. We found it on the closest super-Jupiter to Earth. The one sitting 12 light-years away, the one that, in cosmic terms, we are practically touching. If the closest giant planet to our solar system is already hiding machinery we cannot predict, how wrong are our models for the ones we cannot see as clearly? But the ice clouds are just the beginning. They are the appetizer. The main course is stranger, darker, and harder to fit into any existing framework. Because while the team studying Epsilon Indi Ab was finding frozen architecture in the atmosphere of one super-Jupiter, another team was pointing the telescope at a completely different kind of giant. And what they found there proved that cold ice clouds were the least of our concerns. Meet SIMP 0136. The full designation is SIMP J013656 5 + 0933 47 3. And I promise you that is the last time I will write that out in full. SIMP 0136 for short. And here is the first thing you need to understand about this object. It does not orbit a star. Let that land for a moment. Every planet you have ever been told about orbits something. Mercury orbits the Sunday. Jupiter orbits the Sunday. The exoplanets detected by the Kepler telescope orbit distant stars. Planets, by the definition most of us grew up with, are things that circle stars. That is what planets do. They are born from the disk of gas and dust around a forming star. They coalesce over millions of years, and then they spend the rest of their existence locked in gravitational partnership with the thing that built them. SIMP 0136 does none of this. It drifts. Freely. Through the empty space between stars. Answering to nothing. Bound to nothing. Moving through the galaxy completely alone. 13 times the mass of Jupiter. The size of a small failed star. And just 20 light-years from Earth. Wandering. How does something like this exist? The leading theory is that SIMP 0136 was either ejected from a forming star system during the chaotic early period of its existence, thrown out by gravitational interactions the way a ball bearing gets flicked off a spinning table, or it formed on its own from a collapsing cloud of gas that was too small to ignite into a star. A failed star. A dark sphere of heat and storm, too massive to be a planet, too small to burn, sitting in a category the scientists call a brown dwarf, or a planetary mass object, depending on exactly how the mass calculations resolve. Whatever it is remarkable, and the James Webb Space Telescope decided to stare at it. For 2 full rotations, SIMP 0136 spins quickly. 1 full rotation takes approximately 2.4 hours. The team of researchers, led by Alison McCarthy, a doctoral student at Boston University, used 2 of Webb's instruments simultaneously, the NIRSpec near-infrared spectrograph and the MIRI mid-infrared instrument, to collect thousands of individual measurements of the light coming from SIMP 0136 across the full spectrum of infrared wavelengths. 1 measurement every 1.8 seconds for more than 3 hours. They watched the object turn, watched different faces of its atmosphere come into view, watched the light change as different regions rotated toward them and then away. And what they saw in that data was not what anyone predicted. Let me explain what they expected to see, because the gap between expectation and reality is the entire story here. We knew SIMP 0136 varied in brightness. That had been established years ago by ground-based telescopes and by Hubble and Spitzer. When you look at it across different wavelengths, the brightness goes up and down in a regular pattern. The obvious explanation was patchy clouds. Thick cloud regions making the object appear dimmer when they face you, then the cloud breaks providing a brighter view from below, then thick clouds again, like watching the weather on a giant spinning world. Cloud cover. Wind. The standard toolkit of planetary meteorology. The team expected Webb to confirm the clouds, to give them a detailed view of the cloud layers, maybe resolve their structure, maybe measure their composition. Something clean and expected. A confirmation. Instead, they got 3 completely separate and mutually irreducible atmospheric phenomena happening simultaneously at different altitudes, driven by different physics, producing a combined complexity that could not be explained by any single mechanism in the existing literature. Here is what they found. At the deepest level they could probe, the cloudscape was real but stratified in a way nobody anticipated. Not one cloud layer. Multiple layers at different depths, made of different materials. Deep in the atmosphere, the data suggested clouds made of iron particles. Not metaphorically iron, but literally iron. Iron that has condensed out of the superheated gas at lower atmospheric depths and rained upward as the convective currents carry it. Iron rain falling upward through a world 13 times the mass of Jupiter. Above those iron clouds at shallower depths, evidence for clouds containing silicate minerals, silicates, the stuff rocks are made of, in a planet's clouds, floating there like weather. And then higher still, above both of those cloud systems, a third phenomenon that had nothing to do with clouds at all. Hot spots. Localized regions of anomalously high temperature sitting in the upper atmosphere where the physics of cloud dynamics cannot place them. Regions too hot and too spatially distinct to be explained by solar heating, which is irrelevant anyway because SIMP 0136 has no star. Too hot to be explained by normal heat flowing up from the interior. The leading explanation from the research team is that these hotspots are being driven by one of 2 mechanisms. Either they are upwelling plumes of superheated gas rising from deep in the atmosphere, the way thunderstorm columns push heat upward in Earth's troposphere, or they are auroral. And the word auroral is where this story takes a turn that genuinely changes the picture. Let's talk about what an aurora is on a world with no star. On Earth, auroras happen because our sun constantly fires a stream of charged particles called the solar wind. When these particles hit Earth's magnetic field, they get channeled toward the poles, where they collide with atmospheric molecules and produce the northern and southern lights. The energy of the aurora comes from the sunday, the magnetism shapes it. But the fuel is external. It arrives from outside. SIMP 0136 has no star. There is no solar wind. There is nothing out there sending charged particles streaming toward it. And yet the radio observations made before Webb came along detected what appeared to be auroral activity at SIMP 0136's poles. Bright radio emission consistent with electrons spiraling in a magnetic field, which is exactly the physical mechanism that produces auroras. If there are no external particles to drive those auroras, then the energy has to come from somewhere inside. Some internal mechanism is generating charged particles, accelerating them, channeling them into the poles, and producing radio emission and apparently optical emission in the upper atmosphere, all on its own, in the dark of interstellar space. Think about what you are imagining right now. A planet-sized object 13 times the mass of Jupiter, drifting through absolute emptiness, no star, no external energy source, generating its own light show, producing its own electromagnetic activity, flickering with its own internal fire. We do not have a model for this. We have hypotheses. We have leading explanations that point towards strong internal magnetic fields and interaction with moons or some other co-orbiting body whose existence has not yet been confirmed. But a model that fully accounts for the radio emission and the atmospheric hotspots and their behaviour over time, we do not have one. Webb has revealed a phenomenon operating inside this world's atmosphere that our best physics cannot yet completely explain. And then there was the carbon chemistry. Carbon is the most important element in the universe if you are a living thing. Carbon is the backbone of DNA, of proteins, of every complex organic molecule that constitutes biology. It is the element that makes chemistry interesting. And carbon comes in different molecular configurations. Carbon monoxide, carbon dioxide, methane, each one telling a different story about the temperature and pressure and chemistry of the environment where it formed. In a gas giant atmosphere, carbon chemistry is supposed to be stable. The molecules reach their equilibrium states and stay there. Methane dominates in cool regions. Carbon monoxide takes over at higher temperatures. The transition between them happens at a predictable temperature boundary, and once the chemistry settles, it stays settled. But in SIMP 0136, the carbon chemistry was changing. Not gradually over days or months, over hours. As the object rotated and different faces of the atmosphere came into view, the carbon signatures shifted. The balance between methane and carbon monoxide was fluctuating in ways that the temperature distribution alone could not explain. Different regions of the same atmosphere, at the same time, were showing different carbon chemistry, pockets of carbon dioxide appearing and disappearing. Molecular abundances shifting in ways that implied ongoing chemical reactions, active and dynamic and unstable. "We haven't really figured out the chemistry part of the puzzle yet," said researcher Johanna Voss, one of the co-investigators on the study. That statement, from a scientist looking at Webb's data, is one of the most unsettling sentences in recent astronomy. Not, "we need more data." Not, "our current model predicts this behaviour. We haven't figured it out yet." Because here is what fluctuating carbon chemistry in a giant planet atmosphere actually implies. It implies that the atmosphere is not in equilibrium. It is not sitting at its lowest energy state doing nothing. It is actively being driven by something. The chemistry is being churned. Energy is entering the system and disrupting the molecular balance, and that energy is coming from somewhere, and we do not know where. And the best instruments ever built by humanity are staring directly at it and cannot yet tell us the answer. The atmosphere of SIMP 0136 is, in the words of the researchers, a machine, and the engine of that machine is hidden. Let's step back from the individual discoveries for a moment and look at what these two worlds, Epsilon Indi Ab and SIMP 0136, are telling us together. We have spent decades building a framework for understanding gas giant planets. It started with Jupiter and Saturn in our own solar system. We sent spacecraft to study them. Galileo, Cassini, Juno. Billions of dollars and decades of science designed to unlock the physics of giant planets. We used that data to build models. We validated those models against each other. We refined them. We taught them in universities. We used them to analyze the growing list of exoplanets discovered by Kepler and TESS and other telescopes. By the time James Webb launched, we were confident. Not certain, but confident. James Webb has now looked at 2 super-Jupiter worlds, one orbiting a nearby star, one roaming free, and both of them have contradicted our confident models in fundamental ways. The orbiting one has ice clouds we didn't predict and could not account for. The free-floating one has iron rain, silicate clouds, auroras powered by an unknown internal mechanism, and carbon chemistry so dynamic it is actively changing on a timescale of hours. Neither world matches what the models said we would find. And these are not exotic, distant, extreme objects. Epsilon Indi Ab is 12 light-years away. SIMP 0136 is 20 light-years away. These are our neighbours. In the entire galaxy, which is 100,000 light-years across, these 2 worlds are essentially in our living room. If we are this wrong about what sits in our living room, what are we wrong about in the rest of the house? Here is where the mystery sharpens into something genuinely disturbing. Because the problem with Webb's discoveries is not just that the models were wrong. The problem is what the models being wrong implies about every single prediction we have made downstream from those models. You have to understand the chain of inference in planetary science. Atmospheric models are not just used to understand planets we can directly observe. They are the foundation for everything we say about planets we can barely detect. When a telescope finds an exoplanet by measuring the wobble it causes in its star's motion, we cannot see that planet directly. We infer its size, its mass, its orbital parameters, and then we run it through atmospheric models to predict what its surface conditions might be, what temperatures it might have, whether liquid water is theoretically possible, whether it falls in the so-called habitable zone. The habitable zone, that concept, the region around a star where temperatures might allow liquid water on a planet's surface, the region we search for, potentially life-bearing worlds, the zone that forms the primary criterion for flagging a planet as interesting for follow-up study. The habitable zone calculation depends on understanding how planetary atmospheres work, how they trap heat, how clouds affect albedo, how atmospheric chemistry changes energy absorption. The very models that Epsilon Indi Ab just invalidated by hiding its ammonia behind ice clouds we did not predict. Think about that chain. If our atmospheric models for cold gas giants are wrong because they do not account for thick water ice clouds, then our models for all planets might be missing similar complexity. The ice clouds on Epsilon Indi Ab reflect light back into space, changing the planet's energy budget in ways the simplified models did not include. If similar complex cloud dynamics are operating in the atmospheres of potentially habitable planets, if cirrus-like ice clouds are deflecting sunlight in ways our models ignore, then our predictions about which planets might be hospitable to life could be systematically wrong. We might be pointing telescopes at dead worlds we have classified as promising and missing, living worlds we have classified as too hot or too cold. The stakes of getting atmospheric models right are not merely academic. They are the difference between finding life and missing it, between searching in the right place and spending centuries looking in the wrong place. Let's talk about the second major implication, because this one is closer to home, literally. There is a planet in our solar system that astronomers call a cold gas giant with a complex atmosphere. It has bands of cloud. It has massive storm systems. It has auroral activity at its poles that scientists have studied with Hubble and Juno. It has carbon chemistry that is still yielding surprises every time we look more carefully. That planet is Jupiter. Our Jupiter, the 5th planet from the Sunday, the largest planet in our solar system, the gravitational anchor that helped sculpt the architecture of everything orbiting our star. The planet whose gravity has, over billions of years, acted as a partial shield for the inner solar system, absorbing or deflecting comets and asteroids that might otherwise have struck Earth with extinction-level frequency. The planet whose existence is, in the view of some planetary scientists, a prerequisite for the survival of complex life on Earth. Here is what Webb's discoveries about superjupiters mean for our understanding of Jupiter itself. Jupiter is not as cold as Epsilon Indi Ab. It is considerably colder than SIMP 0136. 0036. But it sits in a temperature regime where similar atmospheric physics applies. The same cloud dynamics, the same chemistry transitions, the same interplay between deep convection and upper atmosphere behavior. The Juno spacecraft has been orbiting Jupiter since 2016, sending back data that has already revealed that Jupiter is far more complex than we thought. The belts and zones of its visible atmosphere, which we assumed extended perhaps 100 kilometers deep, actually penetrate 3,000 kilometers into the planet. The interior is not the simple layered structure we expected. The magnetic field is asymmetric in ways our models did not predict. Now Webb is showing us that Jupiter-like objects are harboring cloud systems we cannot predict, internal energy sources we cannot fully explain, and chemical dynamics we cannot yet model. We have one spacecraft orbiting Jupiter. We have one mission, one snapshot of one solar system's giant planet. And the universe is telling us, clearly and loudly through the data from Webb, that giant planets are more complex than any model we have built for them. Here is the thought experiment that keeps the researchers up at night. If Jupiter has hidden complexity comparable to what Webb found in SIMP 0136, if there are atmospheric dynamics and chemical transitions and deep structural features we are completely misrepresenting in our models, then our predictions about Jupiter's long-term stability are unreliable. And if Jupiter's stability is less certain than we believe, then the stability of the entire solar system's architecture is less certain than we believe. Jupiter is not just a planet. It is a gravitational machine that has been fine-tuning the inner solar system for 4.5 billion years. An object we do not fully understand, sitting at the center of our survival story, showing us through its cousins in deep space that it may be harboring secrets we have not yet found. Here is a third discovery buried inside the Webb data on SIMP 0136 that deserves its own moment of silence. The fact that a world this massive can drift through interstellar space completely alone. We think of planets as things that belong to stars. That is not just a cultural assumption. It is embedded in the scientific definition. The International Astronomical Union's formal definition of a planet includes the requirement of orbiting the Sunday. There are separate designations for objects like SIMP 0136, things like planetary mass object and rogue planet, but even those terms have debate around them. The scientific community is not fully settled on what to call these things, but here is what the existence of SIMP 0136 and objects like it implies about the formation of the galaxy. It implies that the process of planet formation is wasteful, chaotic, violent. It implies that forming star systems routinely build planets that they then eject, throwing them out into the dark at velocities high enough to escape the parent star's gravity forever. Or that clouds of gas collapse into objects too massive to be planets and too small to be stars, creating dark, wandering bodies that populate the space between stars in numbers we cannot yet estimate. How many are there? How common are rogue planets in the galaxy? We genuinely do not know. Some estimates suggest there may be billions of them. More rogue planets drifting through the Milky Way than there are stars. A dark population of lonely worlds that we have only just begun to detect, moving through the void in ones and twos, and perhaps in much larger numbers, invisible to optical telescopes because they emit no visible light, detectable only in infrared by instruments powerful enough to see their faint residual heat. 20 light-years away. SIMP 0136 is 20 light-years away. That is close enough that the sun's light, the light leaving our star right now, will reach SIMP 136 inches 20 years. That means the light currently illuminating the room you are sitting in will wash over a world 13 times the mass of Jupiter in the year 2046, 20 years from now. Close. It is so close. And we did not know it was there until 2006. It was discovered less than 20 years ago. A world 13 times the mass of Jupiter, 20 light-years from Earth, invisible to us until our instruments finally became sensitive enough to detect its infrared glow. How many more are we not seeing? What else is out there, close enough to reach in a single human lifetime at any meaningful fraction of the speed of light, sitting in the dark, unknown, warming itself on its own internal heat, harbouring storms and ice and auroras and chemistry we cannot predict? Let's move to the fourth discovery from these observations, one that the researchers themselves describe as an open question about the underlying physical cause. That phrase, from scientists, in a formal paper, is a polite way of saying something more direct. We do not understand this. Here is the specific phenomenon they are describing. Across the cold giant planets that JWST has now studied, including Epsilon Indi Ab and other cold exoplanets, there is a consistent pattern in the infrared. All of them appear fainter than the models predict in the wavelength range between 3 and 5 microns. This is not a measurement artifact. It is too consistent across too many objects observed with too many different instrument configurations to be an error in the data. Something about how these worlds emit infrared light between 3 and 5 microns is being suppressed. The models say the planets should be brighter here. The data says they are dimmer. Something is blocking or absorbing that specific range of infrared emission. The working hypothesis is that the water ice clouds found on Epsilon Indi Ab are responsible. That similar clouds may be universal features of cold giant planets, not exceptions, and that our simplified models have been systematically wrong because they left out a fundamental component of the atmospheric physics. The clouds are eating the signal. But here is what makes this more than an atmospheric modelling problem. The infrared wavelength range between 3 and 5 microns is one of the primary ranges used by telescopes, including Webb, to study the atmospheres of potentially habitable planets. When we look at a planet and analyse the light filtering through its atmosphere, we use this range to look for specific chemical signatures: water vapour, carbon dioxide, methane. The biosignatures that would tell us whether chemistry is happening that requires biology to sustain. If a class of clouds that we did not know existed can suppress emission in this wavelength range, then our ability to read the atmospheric chemistry of other planets through this window is compromised in ways we have not yet fully evaluated. We could be looking for biosignatures through a smoky filter and not knowing the filter is there. The researchers are calling this pattern a new open question. That is accurate. But the implications of the open question stretch far beyond the cold giant planets where it was discovered. It reaches into the entire enterprise of atmospheric characterization of exoplanets. And it asks, politely but urgently, how many of the things you thought you knew were you reading through a filter you didn't know existed? Let's stop trying to catalogue the individual discoveries and look at the fifth thing James Webb revealed that is harder to quantify, but perhaps the most significant of all. We didn't know what we didn't know. That sounds circular, bear with me. For 100 years, the trajectory of modern astronomy has been one of increasing confirmation. We make a prediction. We build an instrument to test the prediction. We observe. The data fits the prediction well enough. We refine the model slightly. We make a new prediction. We confirm it. The process has worked. It produced general relativity. It produced the standard model of particle physics. It produced the Big Bang theory, dark matter, dark energy, black holes. Prediction followed by confirmation followed by refinement. A virtuous cycle of increasing understanding. James Webb is breaking that cycle. Not because it is finding errors in our mathematics. The mathematics is fine. The physics equations are not wrong. What Webb is breaking is the assumption that our simplified models are adequate proxies for reality. The assumption that when we model an atmosphere with 10 variables instead of 1,000 because including 1,000 variables is computationally impossible, the 10-variable model is close enough. The assumption that the features we left out of the calculation because they seemed secondary were actually secondary. Epsilon Indi Ab's ice clouds were not secondary. They are the dominant feature of the atmosphere. The thing we left out of the model because it seemed complicated turned out to be the whole point. SIMP 0136's internal aurora, its fluctuating carbon chemistry, its vertically stratified cloud structure, none of these are secondary features sitting at the edges of the physics. They are central to how the object works, and they were completely invisible to every instrument we had before Webb, not because we didn't look, because we didn't have the resolution, the spectral range, the sensitivity, the temporal precision to see them. We were not wrong about giant planets because we made errors. We were wrong because we were looking with instruments that were not good enough to show us the truth, and we did not know it. Which brings us to the most uncomfortable implication of all. If every understanding we built before Webb was built on models too simple to capture reality, and if Webb is now showing us that reality is more complex than those models described, then we have to ask, is Webb itself good enough? Or are we now building a new generation of confident understanding on a new generation of models that are still not complex enough to be true, and we simply won't know until a better telescope shows us what Webb missed. Here is the sixth discovery, and this one is personal. This one lives inside you. You are made of the chemistry of a gas giant. Not metaphorically, literally. The carbon in your DNA, the oxygen in your hemoglobin, the nitrogen in your amino acids, all of it was forged in stellar interiors and distributed through the galaxy by stellar explosions. But the pathway from those raw elements to the complex organic chemistry that constitutes life passes through planetary atmospheres. The chemistry of planetary atmospheres is where simple elements get organized into the molecular precursors of biology, where carbon gets combined with hydrogen and oxygen in configurations that can later, under the right conditions, become interesting to life. We have spent decades assuming we understood gas giant atmospheric chemistry well enough to build a reliable story about how those elements move through the solar system and become available to biology. We assumed the chemistry was predictable, that the models were telling us the truth about what happens in those vast chemical reactors hanging in space. Webb just showed us that the chemistry is not what the models said. The carbon chemistry in SIMP 0136 is active, dynamic, shifting on timescales of hours in ways our models did not anticipate. The ammonia chemistry in Epsilon Indi Ab is being rearranged by cloud systems we did not know existed. The molecular inventory of these atmospheres is more complicated, more variable, and less predictable than any previous instrument revealed. Now ask yourself, if the chemistry in giant planet atmospheres is more complex than we thought, then the chemistry delivered to the inner solar system by the processes that flow through those atmospheres, the chemistry that eventually, over billions of years, contributed to the molecular environment that allowed life to emerge on Earth, is that chemistry also more complex than we thought? Are there molecular configurations, chemical pathways, organic precursors distributed through the solar system by dynamics we have not fully modeled, that played a role in the emergence of life on this planet, that we have never thought to look for because our atmospheric chemistry models told us they shouldn't be there? The ice clouds on Epsilon Indi Ab broke the atmospheric models. The carbon chemistry of SIMP 0136 broke the equilibrium assumption. And the question those breaks open, quietly but unmistakably, is whether our story of how life began on Earth is based on models that are similarly oversimplified. We think we know how we got here. We think we can trace the chemistry back through time, through the solar nebula and the late heavy bombardment and the delivery of organic molecules by comets and asteroids. We think the story is basically settled. But the story was built on models, and the models were wrong about giant planets. Let's bring in the seventh discovery, the one that quietly changes the entire enterprise of searching for life beyond Earth. James Webb is not just a telescope for looking at big things far away. It is an atmosphere reader. When a planet transits in front of its star, the starlight passing through the planet's atmosphere carries a barcode of chemical information. Each molecule absorbs a specific wavelength of light. Oxygen has a fingerprint, methane has a fingerprint, carbon dioxide has a fingerprint, water has a fingerprint. When Webb analyzes that light, it can tell you what the atmosphere is made of, in principle from hundreds of light years away. This is the method we plan to use to search for life. Not radio signals from aliens, not megastructures visible in infrared, biosignatures. Chemical anomalies in planetary atmospheres that biology would produce, but that chemistry alone would struggle to explain. Oxygen and methane, coexisting. Nitrous oxide, the unstable, constantly replenished signatures of a living world. This method is our best plan for finding life beyond Earth in the foreseeable future, and it depends entirely on our ability to accurately read atmospheric chemistry from the light that reaches our telescopes. What Webb found on Epsilon Indi Ab is a direct challenge to that method. The ice clouds that suppress the ammonia signal on Epsilon Indi Ab do so by sitting in the atmosphere and blocking the wavelengths that would otherwise carry the chemical information outward. The clouds act as a blanket over the chemistry below them. When we look at the atmospheric barcode of a planet with these clouds, the barcode is incomplete. Certain lines are missing not because the chemistry is absent, but because the clouds are blocking the signal. If we looked at Epsilon Indi Ab without knowing about the ice clouds, and if we were trying to assess whether its atmosphere matched predictions for a gas giant at its temperature, we would conclude that something fundamental was wrong with the atmospheric composition. We would see a chemical signature that did not match the models, and we might, depending on what specific molecules were hidden and what specific molecules remained visible, misinterpret that mismatch as evidence of something interesting. Something anomalous. Something potentially biological. False positives. Webb's discovery of unexpected clouds in gas giant atmospheres has introduced the possibility of false positives in the search for biosignatures. Of atmospheres that look chemically anomalous, even potentially biologically interesting, not because anything alive is producing the anomaly, but because a cloud layer we did not know was there is rearranging the barcode. The scientists are very careful, very measured, very precise about this. They do not say that Webb's discoveries mean the biosignature search is compromised. They say it means the models need to be improved. They say it means the cloud physics needs to be better understood before we interpret anomalous atmospheric signals as signs of life. But listen to what that means in practice. Before we can confidently claim that an anomalous atmospheric signal on a potentially habitable exoplanet is evidence of biology, we need to be able to rule out the alternative explanation, clouds we could not see. And to rule out that explanation, we need to understand cloud physics well enough to model it accurately. And according to the data Webb just returned, we do not yet understand cloud physics well enough. The models are wrong. The clouds are more complex and more consequential than anything the models predicted. We are building the biosignature detection strategy on a foundation that has just cracked. This is the point where you might be expecting reassurance, where the narrator says, "But here is the silver lining." And there is one. There genuinely is. But the reassurance comes wrapped in something unsettling that makes it more interesting than a simple comfort. The reassurance is this: we found the error. That is not nothing. It is enormous. The entire history of science is a history of finding errors in what came before, not because the previous scientists were foolish, but because the previous instruments were insufficient. Newton's gravity worked until we built instruments precise enough to see the precession of Mercury's orbit and required Einstein to explain it. The steady-state universe seemed reasonable until we built radio telescopes sensitive enough to detect the cosmic microwave background and required the Big Bang to explain it. James Webb is that next instrument, the one precise enough to see what was hidden before, and what it is showing us about giant planet atmospheres, the ice clouds, the internal aurora, the carbon chemistry fluctuations, the suppressed infrared emission. All of this is not evidence that the universe is broken. It is evidence that our models were incomplete. And incomplete models, when found to be incomplete, can be fixed. Elizabeth Matthews and her team are already working on it. They are applying for more JWST observation time to study additional cold Jupiter analogues. They are building toward a sample large enough to determine whether the suppressed ammonia feature is universal, whether the ice clouds are everywhere, whether the pattern holds across the entire population of cold giant planets in the galaxy. And NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2026 to 2027, is specifically designed to directly image the reflective water ice clouds that JWST found indirectly. Roman will not just confirm what Webb saw, it will map it. It will give us the full picture of what the cloud systems look like, not just what they do to the chemistry below them. The answer is coming. The correction to the models is coming. And when it arrives, when we have a cloud physics framework comprehensive enough to actually reproduce what Webb is seeing, we will have atmospheric models powerful enough to read the biosignature barcodes of distant planets with the confidence we need to say, this anomaly is real. This is not a cloud. This might be life. That is the prize waiting on the other side of this confusion. But here is the unsettling part of the reassurance. The correction is coming because we found the error, and we found the error because we built Webb. But what errors does Webb itself not have the precision to find? What complexity in planetary atmospheres is sitting just below Webb's detection threshold, waiting for the next telescope, the one that will look at Webb's results the way Webb looked at Hubble's, and say, the models were wrong again, look at what was hidden. The lesson Webb is teaching us is not specifically about giant planets. It is about the relationship between instrument capability and understanding. It is about how confidently we should hold any model built on any instrument's data. It is about whether scientific understanding is an asymptotic approach to truth, getting closer but never quite arriving, or whether there are fundamental limits on what any finite instrument can reveal about an infinitely complex reality. We like to think that science converges, that each new telescope shows us more of the picture, and eventually the picture is complete. But Webb is showing us that each new telescope shows us that the picture is bigger than we thought. Every new instrument does not narrow the remaining unknown, it expands it. Not because reality is getting more complex, because we are finally seeing enough of it to realize how much we were missing. Let's sit with the full weight of what we have covered tonight, because it is heavier than the individual discoveries suggest. James Webb pointed at a super-Jupiter called Epsilon Indi Ab and found ice clouds that the models said should not be the dominant atmospheric feature. The models were wrong. The ice clouds are so thick and so complete that they buried the primary chemical signature of the atmosphere and rendered every previous prediction about this planet's atmospheric composition inaccurate. James Webb pointed at a free-floating super-Jupiter called SIMP 0136 and found multiple overlapping atmospheric phenomena: iron clouds, silicate clouds, high-altitude hotspots, aurora-driven energy deposition, and fluctuating carbon chemistry, none of which can be explained by any single mechanism, and several of which have no fully resolved physical explanation. Together, these two worlds have broken the models we use to understand all cold, giant planets. They have introduced uncertainty into the biosignature detection strategy that represents humanity's best current plan for finding life beyond Earth. They have revealed a class of world, the free-floating planetary mass object, far more dynamically active than anyone predicted. And they have established, with the most sensitive telescope ever built, that the atmospheric chemistry of giant planets is a three-dimensional, temporally variable, mechanistically complex system that we have not yet learned to model correctly. That is a lot of wrong. And yet, and here is where you have a choice about what to do with all of this wrongness. You can feel the weight of it and buckle. You can decide that if the universe is this much more complex than our best models predict, then understanding it is hopeless, and we should stop pretending we are making progress. Or you can feel the weight of it and stand up straighter, because the weight of what we do not know is not evidence of failure, it is evidence of seriousness. Of a species that cares enough about the truth to build $10 billion instruments and point them at the sky, and let the data break whatever comfortable assumptions were in the way. Every model that Webb has broken was a model we needed to be broken. Every assumption that turned out to be oversimplified was an assumption that was slowing us down. The ice clouds on Epsilon Indi Ab are not a crisis. They are a correction. The fluctuating carbon chemistry of SIMP 0136 is not a catastrophe. It is a gift. It is the universe saying, here is something real. Here is what is actually happening. Now update your picture. You want to know the most extraordinary thing about what these discoveries mean, not for planetary science, not for the search for life, but for you, specifically, sitting in the room you are in right now. The planet Epsilon Indi Ab exists 12 light-years away. The light leaving it right now will take 12 years to reach us. The data that Webb collected about its atmosphere left that planet around the time we were building the instruments to detect it. We are receiving a message from a cold gas giant in slow motion, delayed by the finite speed of light, arriving in our instruments after a journey of 12 years. SIMP 0136 is 20 light-years away. The light from its aurora, its hotspots, its churning carbon chemistry, it is travelling toward us right now, and will arrive in 20 years, and we will not know it is different from the data we collected in 2023, because nothing will have announced the change. We are watching a world in real time, but the real time we see is 20 years ago. You are looking into the past every time you look at the sky. Every single object you see is history. The sun is 8 minutes old, the moon is a little over a second old, Jupiter is about 40 minutes old, and the super-Jupiters that James Webb is studying are 12 to 20 years old. The storms on them that we are watching may have dissipated. The clouds may have changed. The aurora may have shifted or intensified or gone dark. We are conducting science on a universe we can only see in snapshots. We are studying dynamic systems through a time delay that ranges from seconds to billions of years. And somehow, through the mathematics of spectroscopy and orbital mechanics and thermodynamics, we are extracting true information about how those systems work despite never seeing them as they are right now. That is remarkable. It is a triumph of human intelligence and human persistence and human humility. We built instruments that cannot see the present moment of a world 12 light-years away. So instead we built the mathematics to extract the physics from the past, and the physics tells us what the present must look like. And then Webb goes and looks and finds that the mathematics was based on models that were missing ice clouds. And instead of giving up, the scientists apply for more telescope time. But let's press on the bruise of that wrongness for a little longer, because there is a specific kind of wrong that is worse than being simply incorrect. There is the kind of wrong where you are not just missing a detail, you are missing the organising principle. And that is the kind of wrong that James Webb has found at the heart of how we study planetary atmospheres. Here is what I mean. When scientists build an atmospheric model, they are not just making guesses, they are encoding physics. They are taking the laws of thermodynamics, quantum mechanics, radiative transfer, and fluid dynamics, and they are combining them into a simulation that is supposed to replicate the behaviour of a real atmosphere. The simulation has never been complete. It cannot be. The real atmosphere of any planet contains billions of variables operating simultaneously at every scale, from the subatomic to the planetary. No computer can track all of them, so scientists make choices. They include the physics they believe is dominant, and they approximate everything else. The assumption encoded in those choices is this: the physics we are leaving out is secondary. It contributes at the margins. It modifies the results slightly but does not fundamentally change the answer. Epsilon Indi Ab proved that assumption wrong at the most basic level. The ice clouds were not a marginal correction. They were not a 5% modification to the ammonia signal. They suppressed the ammonia signal so completely that the dominant chemical feature of the atmosphere was invisible. The thing that was left out of the model was not a decoration on the edges of the physics. It was the physics. It was the central player in the atmospheric system, and the models had deleted it for simplicity. This is what scientists call not a quantitative error, but a qualitative error. You are not wrong by a factor of 2. You are wrong about which thing matters. That is a different and deeper kind of wrong, and it is harder to fix. Fixing a factor of 2 means refining your calculations. Fixing a qualitative error means rebuilding the framework. The atmospheric science community is now rebuilding the framework. And while they do, everything built on the old framework is suspect. Every paper that used the old models to predict the atmospheric properties of cold giant planets has to be re-examined. Every conclusion drawn from those predictions about which planets might be habitable, about which atmospheric chemistry signatures are anomalous, about which worlds deserve follow-up observation because they showed something unexpected, all of it now carries an asterisk. Not because the scientists were wrong to trust the models were the best available, but because the best available was not good enough. And we now know it, and we cannot unknow it. There is a concept in philosophy of science called the theory-ladenness of observation. It means that what you see when you look at something depends on the theoretical framework you bring to the observation. You do not see raw data. You see data interpreted through a lens. The lens is the model. The model shapes what counts as a signal and what counts as noise, what counts as interesting, and what counts as expected. When Hubble looked at Epsilon Indi Ab before Webb, it was looking through a lens built from simplified atmospheric models. Those models said the dominant features to look for were ammonia and methane. So the instruments were configured to look for ammonia and methane. The ice clouds were there. They were always there. But they were not the thing the lens was focused on, and so the lens did not resolve them clearly enough to identify them. Webb has better resolution, wider wavelength coverage, higher sensitivity, a better lens. And with a better lens, the ice clouds became unmistakable. But here is the uncomfortable implication of theory-ladenness. Webb is also looking through a lens. It is looking through models. Its instruments were designed. Its filters were chosen. Its observation programs were planned based on what scientists expected to find. Webb is smarter than Hubble. It is more powerful. Its lens is sharper. But it is still a lens. What are the ice clouds of James Webb? What are the things that the current generation of models has taught us to look past, to categorize as secondary, to approximate away? What is the thing that the next telescope, Roman or the Habitable Worlds Observatory or whatever comes after that, will point at Webb's data and say, it was right there in every spectrum, but the models told you it was noise? This is not a rhetorical question. It is a genuine scientific concern. The researchers who discovered the ice clouds on Epsilon Indi Ab are explicitly saying, the models were too simple. We need more complex models. We need cloud physics in the simulations. But the models they are building to replace the old ones, the new, more complex models, those models will still be simplified. They will still be making choices about what physics to include and what to approximate. They will still be a lens. The history of astronomy is a history of successive better lenses, each one revealing things the last one could not see, and each revelation demonstrating that the next lens will need to be better still. There is no final lens. There is only the current best lens, and the humility to know it is not the last one. Now let's talk about something that sounds technical but has an implication so personal it might change how you feel about the night sky. SIMP 0136's rotation period is 2.4 hours. That number is worth dwelling on. Our Jupiter rotates in about 10 hours, which is already the fastest rotation period of any planet in our solar system. The Earth takes 24 hours. SIMP 0136 completes a full rotation in 2.4 hours. It is spinning so fast that the equator of this world, which is substantially larger than Jupiter, is moving at an enormous velocity. The centrifugal force at the equator is significant enough to measurably distort the shape of the object, flattening it at the poles. And as it spins, the different faces of its atmosphere come in and out of view, each one slightly different from the last, each one carrying a different weather pattern, a different cloud configuration, a different chemical balance. The Webb observations watch 2 complete rotations, 4.8 hours of continuous data. Every 1.8 seconds, a new spectrum. Thousands of snapshots of a world turning. What did those snapshots show about the weather? They showed weather that would make anything on Earth look calm. At the deepest atmospheric level Webb could probe, the iron clouds. Iron clouds are not a metaphor or a simplification. The temperature and pressure at certain depths in the atmosphere of a giant like SIMP 0136 are extreme enough that iron, metallic iron, vaporizes and rises in convective columns. As those columns rise into cooler layers of the atmosphere, the iron vapor condenses and forms particles. Tiny solid or liquid droplets of iron, forming cloud banks that drift in the atmosphere the way water clouds drift in our own sky. Except instead of white cumulus, these are clouds made of metal. Dark, dense, exotic, and enormous, sweeping across the face of a world no human eye has ever directly seen. Above the iron clouds, at higher altitudes, the silicates. Silicates are the mineral family that includes quartz, olivine, pyroxene, the stuff that makes up the rocks on Earth's surface and the interior of terrestrial planets. In SIMP 0136, silicates are not rocks, they are clouds. At the temperatures and pressures in the mid-atmosphere of this giant, silicate minerals are in vapor form, condensing into particles that form cloud layers. Silicate grains, each one a microscopic piece of what on a rocky planet would be the ground, floating in the atmosphere of a rogue giant, forming weather that moves and shifts and changes from hour to hour. And above the silicates, the hotspots, bright, localized regions of elevated temperature that move across the planet's face as it rotates. Some of them are consistent with being high-altitude upwellings, columns of hot gas rising from deep in the atmosphere and breaking through into the upper layers before cooling and sinking back down. The planetary equivalent of cumulonimbus thunderstorm columns on Earth, except each one of these columns is potentially the size of a continent. Some of the hot spots are consistent with auroral activity, with magnetic field lines channeling charged particles into specific atmospheric regions and depositing energy there, heating the gas locally and causing it to glow. Except there is no star providing the charged particles. Whatever is driving the aurora is internal to the object itself. And through all of this, the carbon chemistry is shifting. The balance between methane and carbon monoxide and carbon dioxide is fluctuating as different parts of the atmosphere rotate into view. The chemistry is not at equilibrium. Something is constantly pushing it away from equilibrium, and different regions are being pushed in slightly different ways. This is what a gas giant actually looks like when you can see it clearly enough. Not the smooth, banded, predictable gas ball that a simplified model describes. A three-dimensional, dynamically churning, chemically active machine, layered and turbulent and strange. Nothing about it sits still. Nothing about it is simple. And yet we have been using simplified models to understand our own Jupiter, the Jupiter that sits in our solar system, the Jupiter we have spacecraft orbiting right now, the Jupiter whose atmospheric dynamics we have been studying for decades. Are we missing the iron clouds in Jupiter's deep atmosphere? Not literally iron. Jupiter is too cold for that, but the equivalent class of deep exotic cloud layer that our simplified models have left out. Are we missing the aurora-driven hotspots in Jupiter's upper atmosphere? Are we missing the fluctuating carbon chemistry that might be operating in the regions below the cloud tops that Juno cannot yet probe? We do not know, and not knowing is the entire problem. Here is something you almost certainly have never thought about, but once you hear it, you will not be able to stop thinking about it. The super Jupiters that James Webb is studying are, in a very real sense, the most important objects we can observe for understanding the origins of our own solar system. Here is why. Our solar system formed roughly 4.6 billion years ago from a collapsing cloud of gas and dust. The early solar system was chaotic. There were likely many more planetesimals, protoplanets, and perhaps additional giant planets than exist today. The giant planets migrated. Jupiter may have moved significantly inward from where it formed before being pulled back outward by Saturn's gravitational influence. This migration and the gravitational interactions between the forming planets shaped the architecture of everything: the asteroid belt, the position of Mars, the conditions in the inner solar system that eventually produced a planet where liquid water could exist on the surface. The history of Jupiter's formation and early migration is encoded in the structure of the solar system we live in. Understanding that history requires understanding how Jupiter formed. And understanding how Jupiter formed requires understanding the physics of gas giant planet formation and early evolution. And that physics is written in the atmospheres of the super Jupiters that Webb is studying. Epsilon Indi Ab is young enough and warm enough from its formation heat to be a window into an earlier stage of Jupiter-like evolution. Its atmosphere is showing us what a giant planet looks like before it has fully cooled down from its formation. The ice clouds we found there, the patchy water ice structures hiding the ammonia chemistry below, those clouds may be telling us something about the atmospheric dynamics that Jupiter went through during its own early history. SIMP 0136 is younger still in some respects. As a free-floating object, it has been cooling since it formed, and its current temperature of approximately 825 degrees Celsius at deeper atmospheric levels is hotter than Epsilon Indi Ab. It sits in a different temperature regime, one where the cloud composition is different, where iron and silicates dominate rather than water ice. But the dynamical complexity, the layered clouds, the chemical activity, the internal energy driving the aurora, that complexity is telling us something about the physical processes that operate inside any massive gas giant at any stage of its evolution. Jupiter today is cold. Epsilon Indi Ab is at an intermediate temperature. SIMP 0136 is hotter still. Together they form a sequence, a timeline of gas giant cooling, captured in 3 different objects at 3 different stages of evolution. Webb is giving us the ability to read that timeline in atmospheric detail for the first time. What that timeline is revealing is that gas giant atmospheres are never simple. At every stage of cooling, at every temperature regime we can observe, the atmosphere is more complex than the models predicted. The complexity changes form, the cloud composition changes, the dominant chemistry changes, but the fundamental character, layered, dynamic, internally driven, chemically active, remains. This is not what the simplified models predicted. The simplified models predicted that as you move through different temperature regimes, gas giant atmospheres should exhibit predictable, cleanly transitioning behaviors. That at each temperature there is a dominant chemistry and a dominant cloud type, and the transition between regimes should be sharp and clear and calculable. The data says the transitions are messy. The atmospheres are complicated at every temperature. And the complications at each temperature are different from the complications at the next temperature in ways that require new physics to explain. Let's ask the question that the data is pointing toward but that the scientists are too careful to state outright. If every gas giant we look at closely has atmospheric complexity that the simplified models missed, and if the simplified models were the basis for our predictions about which planets might be habitable, and if those predictions are now suspect, then how many of the planets we have dismissed as uninhabitable over the last 20 years of exoplanet discovery were dismissed based on incorrect atmospheric models? How many times has a telescope found a planet orbiting in the habitable zone of its star, run its atmospheric chemistry through the models, found nothing anomalous, and filed it away as unremarkable? No further observation needed, when the reality might have been that a thick cloud layer the model didn't account for was burying the anomalous chemistry we would have found interesting. And the reverse. How many times has a telescope found an atmospheric anomaly in a planet outside the habitable zone, flagged it for further observation because the chemistry looked unusual, and sent scientists down a research rabbit hole, when the reality was that the anomaly was an artifact of a cloud system the model didn't include? We cannot answer these questions yet. That is the point. Before Webb, we did not know the models were wrong in this way. We could not ask whether the conclusions drawn from those models were reliable because we had no way to test the models against real high-resolution atmospheric data from the relevant kinds of planets. Now we do. And the first tests have failed. The research community is being careful and measured in how they talk about this. They say the models need to be improved. They say these are exciting findings that will drive better science. They say the field is moving in the right direction. All of that is true. But underneath the careful language is the reality. There is a gap between what we thought we knew and what we actually know. And the gap is in the foundational tool used to interpret atmospheric data from the vast majority of planets we have studied. And we are only just now learning the full dimensions of that gap. Let me tell you about Elizabeth Matthews for a moment, because she is the person whose name is on the paper that broke the models. She is a researcher at the Max Planck Institute for Astronomy in Heidelberg, Germany. She led the first JWST observation of Epsilon Indi Ab in 2024, a study that was itself already groundbreaking, because it was the first direct image of a cold Jupiter analogue with the Webb telescope. Cold, meaning truly cold, not the hot Jupiters that dominate most exoplanet studies. She was the lead author on both the 2024 discovery and the 2025 follow-up that found the ice clouds. The finding of the ice clouds came from a comparison between two observations taken a year apart at slightly different infrared wavelengths. The 2024 observation used a filter at 10.6 microns, which sits inside the ammonia absorption feature. The 2025 observation used a filter at 11.3 microns, which sits just outside it. By comparing the brightness at these two wavelengths, the team could estimate how much ammonia was present in the atmosphere. The planet was brighter at 11.3 microns than at 10.6 microns. That is expected. What was not expected was how much brighter. The ratio between the two wavelengths implies a much smaller ammonia signature than the models predicted. And when Matthews and her team went through every possible explanation for that deficit, the one that fit the data best was water ice clouds. Thick, patchy, covering large regions of the planet's disk and suppressing the infrared emission from the ammonia below. The models had all been cloud-free, not because anyone thought the planet had no clouds, but because including clouds in models is computationally expensive, and the simplified cloud-free versions had been good enough before. They were not good enough now. They were wrong by a margin that had to be explained, and the explanation required adding to the model the complexity that everyone had agreed to temporarily leave out. Matthews' statement about the result is worth reading precisely. She said that Webb is finally allowing us to study solar system analog planets in detail. Note the word finally. Note the implication that what we could do before did not rise to the standard of detail. Note the humility in acknowledging that the first telescope capable of seeing these worlds clearly has immediately shown us that we did not understand them. That is what science looks like when it is functioning correctly. Not triumphant confirmation, not expected results. A first clear look, followed by surprise, followed by the admission that the surprise is bigger than anticipated, followed immediately by the design of the next observation to understand it better. The next observation is already being planned. Matthews is applying for additional Webb time to study more cold Jupiter analogues. Roman is on the launch pad. The correction to the models is being built right now, driven by data from a telescope that showed us, once again, that the universe is not waiting for us to understand it before it does things we didn't predict. There is a thought experiment that planetary scientists sometimes use with each other informally, not in papers because papers require rigor, but in hallways and over coffee when the data is sitting in front of them and the implications are pulling at the edges of what is safe to say in print. The thought experiment goes like this. Imagine you are an alien civilization. You are technologically advanced. You have instruments comparable to Webb, maybe better. You are conducting a survey of nearby star systems to understand what kinds of planets exist in your cosmic neighborhood. You point your instruments at our solar system. You study our sun's giant planets, Jupiter and Saturn and Uranus and Neptune. You run their atmospheric data through your best models. What do you conclude? Now here is the uncomfortable question. Would those conclusions be right? If our best models of gas giant atmospheric chemistry are wrong by the margin that Webb has just revealed, then an alien civilization with equivalent models would draw wrong conclusions about our solar system. They would see Jupiter and predict its chemistry incorrectly. They would see Saturn and miss whatever cloud systems are hiding signals below its cloud tops. They would look at Uranus with its bizarre polon axial tilt and its ice giant chemistry and apply a model that was calibrated against gas giants, and they would get wrong numbers. And then they might, with whatever detection capability they have, look at Earth. They would look for anomalous atmospheric chemistry. They would look for the signature of a world where something interesting is happening, where chemistry is out of equilibrium in ways that suggest ongoing production of reactive molecules. They would look for the coexistence of oxygen and methane, for the presence of nitrous oxide, for all the biosignatures that life produces. But they would be looking through models, and if their models were as incomplete as ours, if they had the equivalent of our simplified pre-Webb atmospheric framework, they might miss the signal. The biosignatures might be there, clearly visible in the data, and the models might tell the instruments to look elsewhere, to classify the Earth signal as a thermal artifact or an instrument artifact, or simply as within expected range for a rocky planet at this distance from its star. We might be the frozen ammonia chemistry of another civilization's observations. We might be the ice cloud they didn't know was there, hiding the signal they were looking for. This is not a comforting thought, but it is a rigorous one. We are learning right now, from Webb's data on superjupiters, that the relationship between atmospheric data and the conclusions drawn from that data is less reliable than we thought. We are learning that models miss important things. We are learning that signals get hidden by phenomena we did not include in the simulation. If that is true for us looking at other worlds, then by symmetry it may be true for any other civilization looking at us. And the silence of the cosmos, the absence of confirmed biosignature detections, the lack of any clear chemical flag in any exoplanet atmosphere that says definitively this world is biologically active, that silence might not be evidence of emptiness. It might be evidence of incomplete models, our incomplete models, or the incomplete models of anyone else who might be looking. There is one more thing that Webb's super-Jupiter discoveries tell us that deserves its own space, and it is something that brings the entire story back to a place that is personal rather than abstract. Science is not a building, it is a conversation. We teach science as if it were a building. We stack the facts like bricks. We say, Galileo discovered moons around Jupiter. Newton derived the law of gravity. Einstein corrected Newton. Time. Hubble measured the expansion of the universe. Each generation adds to the structure, and the structure grows higher and more stable. The bricks at the bottom are load-bearing. They do not change. You can trust them. But the discoveries Webb is making about superjupiters are not bricks getting added to the top of the building. They are discoveries that are reaching down into the existing structure and finding that certain bricks at the middle levels were the wrong shape, not wrong at the foundation. The physics equations are fine, but wrong in the middle, in the translation layer between the fundamental physics and the applied models, in the choices made about what to include and what to approximate, in the confidence placed in simplifications that turned out to be too simple. This is not unprecedented in science. It happens. The history of science is not a smooth upward trajectory. It is an irregular climb with occasional discoveries that require not just adding to what we know, but revising how we have been using what we thought we knew. The discovery of quantum mechanics did not just add information to classical physics. It revealed that classical physics was missing something fundamental about the behavior of matter at small scales. The discovery of DNA did not just extend biology. It revealed that the entire understanding of how traits are inherited was incomplete. Webb's discoveries about giant planet atmospheres are in that category, not as sweeping as quantum mechanics or DNA, but the same structure. A revelation that the existing framework was missing something fundamental, and that the missing thing was not peripheral but central to how the whole system works. The conversation continues. The conversation always continues. And the next time someone speaks in this conversation will be when Roman launches and directly images the water ice clouds that Webb could only infer. Will be when the next set of cold Jupiter observations comes back and the researchers test whether the suppressed ammonia feature is universal. Will be when a theorist somewhere works out the mechanism driving the carbon chemistry fluctuations in SIMP 0136 and writes a paper that starts with the words, "We now understand what was happening." That paper will be written, the understanding will arrive, the models will be corrected. The framework will be rebuilt with the ice clouds included, with the iron rain accounted for, with the aurora physics properly represented, and the new framework will be better, more accurate, closer to the truth. And then Webb, or Roman, or the next telescope will look at something new, and the data will come back showing something that the new, improved, corrected models did not predict. And the conversation will take another turn. This is not failure. This is the mechanism. This is how the conversation moves. This is how we inch our way toward a description of reality that is less wrong than the one before it. You are watching it happen in real time. The models broke this week. The ice clouds arrived in the data. The carbon chemistry shuffled its molecular deck in front of the instruments. And somewhere right now, a scientist is sitting in front of a screen, looking at the numbers and feeling the specific sensation that every person who has ever made a genuine discovery has felt. The sensation of reality pushing back against assumption, of the data refusing to fit the box, of the universe declining to behave the way the textbook said it would. That sensation is the heartbeat of science. It feels like confusion, but it is actually clarity. It feels like failure, but it is actually progress. 2. It feels like the ground giving way, but it is actually the old ground being replaced by something more solid. We have established that giant planet atmospheres are more complex than any model predicted. We have established that ice clouds can bury chemical signatures, that iron can reign in the atmosphere of a rogue world, that auroras can be powered by internal mechanisms we do not fully understand, that carbon chemistry can be dynamic and variable and actively driven by processes we have not identified. And we have established that these discoveries reach far beyond the superjupiters themselves. They reach into the biosignature detection program, into our understanding of Jupiter, into the story of how our solar system formed, into the question of how reliably any telescope can read the chemistry of a distant world when the models interpreting the data are incomplete. That is the full weight of what the James Webb Telescope found when it stared inside a superjupiter. But here is what I want you to take away from all of this, because the story should not end in the weight of what we do not know. The story should end where the scientists themselves have placed it, in the extraordinary privilege of being the species that built the instrument that made the discovery. We are the only part of the universe, as far as we know, that is aware of itself. We are the only arrangement of matter that can point a mirror at the cosmos and ask what is there. And we built a mirror good enough to see ice clouds 12 light years away. Good enough to watch the weather turn on a rogue world drifting alone in the interstellar void. Good enough to detect the aurora of a planet with no star. We built that mirror with hands and mathematics and decades of work and $10 billion and a collective act of human will that required thousands of people across dozens of countries to believe that the question was worth the cost. And we launched it on Christmas Day, 2021, and it unfolded perfectly in the cold dark of space, one terrifying mechanical step at a time, and it started sending back data. And the data broke the models. And the scientists didn't panic. They published. They applied for more telescope time. They started building better models. They described what they found with precision and honesty and the specific kind of excitement that looks, from the outside, like calm professionalism but is actually, internally, the experience of seeing something no human has ever seen before and understanding for the first time what it means. There is one more layer to excavate before we get to the final one, and it lives in the word closest. Epsilon Indi Ab is described, repeatedly, in the scientific literature as the closest superjupiter to Earth. The closest, the nearest, the one sitting just down the cosmic street. And that designation matters more than it might first appear. Here is why. In astronomy, there is a hierarchy of observational quality that is simply a function of distance. Closer objects are brighter. Closer objects are easier to resolve spatially. Closer objects can be studied with instruments that would fail entirely on objects farther away. The closest superJupiter is not just interesting because it is nearby. It is interesting because it is the one we can study in the most detail. The one where our instruments can collect the most photons, the most spectral information, the most data per observation. The one that gives us the highest signal-to-noise ratio and the best chance of extracting the truth about what is happening in its atmosphere. And the closest superJupiter, the one we can see in more detail than any other, is the one whose atmosphere is hiding its chemistry behind ice clouds that the models didn't predict. If the best-case scenario, the most favourable, most observable cold giant exoplanet in our stellar neighbourhood, is already showing us that the models are inadequate, what are we to conclude about the cold giant exoplanets that are 10 times farther, 100 times farther? The ones where our signal is weaker, our photon count is lower, our ability to distinguish between the real atmospheric signal and noise from the model's assumptions is reduced? The answer is that we have been drawing conclusions about those distant worlds from a model that we now know is wrong, with less data to catch the error and less ability to correct it, even if we suspected the problem. The discoveries at Epsilon Indi Ab, the closest and most observable target, are our best-case scenario for detecting this kind of atmospheric complexity. At every other cold giant exoplanet we have studied, the situation was worse. The data was noisier. The model's fingerprints on the conclusions were heavier. The gap between what the data actually says and what the model trained us to see was bigger. We are not just correcting one planet's atmospheric description. We are opening the question of how many atmospheric descriptions we have gotten wrong that we cannot yet re-examine because the signal is too weak and the better models are not yet built. That is not a counsel of despair, it is a counsel of precision, of humility, of the awareness that the database of exoplanet atmospheric characterizations built over the last decade has to be held more lightly than we were holding it. Not thrown out, not dismissed, but held with the knowledge that the models underpinning the interpretations were missing something we have only just identified, and that the most important question in exoplanet science right now might not be, what is the atmosphere of planet X made of? It might be, how much of what we think the atmosphere of planet X is made of is real, and how much is model artifact? That is a hard question to live with. Science is uncomfortable when its confidence has to be revised downward. The transition from we know to we think we know but the models may be missing something is not a pleasant one, but it is an honest one. And honesty, even uncomfortable honesty, is the only currency science actually has. There is one final implication of these discoveries that we have to sit with before we close. It is not comfortable, and it has no immediate resolution, but you need to carry it with you because it is true, and because it changes what it means to look at the sky. We have spent this entire time talking about what is wrong, what the models missed, what the data broke, what the clouds are hiding, what the aurora does not explain. And all of that is real and important and worth sitting with. But here is the other side of the ledger, and I want you to feel both sides before we finish. Everything that was wrong in the direction of reality being more interesting. Think about that. The models predicted simple atmospheres. The reality turned out to be complex ones. The models predicted clean, predictable chemistry. The reality turned out to be dynamic, active, shifting chemistry. The models predicted that the dominant atmospheric signatures would be clearly readable. The reality turned out to be that thick, structured, layered cloud systems were hiding the chemistry and reorganizing the atmosphere in ways nobody anticipated. In every case, the universe chose to be more interesting than we expected, more layered, more active, more dynamically alive, not simpler and more boring than predicted. More complex and more surprising than predicted, every correction to the models is a correction in the direction of greater richness, greater complexity, greater strangeness. If you had to bet, before we had any data from Webb, on whether the universe would turn out to be more interesting or less interesting than the simplified models suggested, which would you have chosen? Most people asked that question would bet on more interesting, because the history of every scientific instrument improvement has been a history of finding more interesting things. Galileo's telescope found moons around Jupiter, when the pre-Copernican model said the sky was perfect and simple. Hubble found that the universe is expanding, when the pre-relativistic model said it was static. Every increase in observational power has been repaid with increased complexity, increased strangeness, increased surprise. Webb is no exception. It is a continuation of the pattern. More resolution, more sensitivity, more spectral range. More complexity revealed, more models broken, more of the universe's actual machinery made visible. And the machinery is magnificent. Iron clouds raining through the atmosphere of a rogue world. Ice clouds frozen at the boundary between ammonia chemistry and the deep heat of a cooling giant. Aurora painting the poles of a free-floating colossus in the dark between the stars. Carbon molecules reshuffling their configurations as the planet turns, driven by processes that no model yet explains. This is what the solar neighborhood actually contains, not the smooth, predictable gas balls that the simplified models described. These wild, turbulent, layered, internally energetic, chemically active engines of weather and aurora and cloud and storm, sitting 12 and 20 light-years from the planet where you are right now reading about them. Close enough that every photon web collected from their atmospheres completed most of its journey to our detectors during your own lifetime. The universe is not waiting to be understood. It is not sitting still while we figure it out. It is active and strange and more complex than any model we have yet built for it. And every now and then we build an instrument good enough to see a little more of what it actually is. James Webb is that instrument. And what it saw inside a super Jupiter was not a confirmation of what we thought we knew. It was an invitation. An invitation to look again, more carefully, with better tools and less confidence in the models, and more curiosity about what the data is actually saying underneath the assumptions. We did not go to the expense and effort and genius of building this telescope to have it confirm the textbook. We built it to show us what the textbook missed. And it is doing exactly that. The ice clouds are real. The iron rain is real. The aurora without a star is real. The chemistry that shifts every 2 hours on a rogue world, 20 light-years from Earth, is real. And we are the species that found it. Alison McCarthy's study of SIMP 0136 included a statement that will define a research program for years. She said, "We haven't really figured out the chemistry part of the puzzle yet. The chemistry of a world 13 times the mass of Jupiter, 20 light-years from Earth, is changing on a timescale of hours in ways that cannot be explained by the physics we currently understand. We are watching it happen. We have the data. We can see the fluctuation in the carbon signatures as different faces of the atmosphere rotate into view. We cannot explain it. This is different from the ice clouds on Epsilon Indi Ab. The ice clouds were unexpected, but the physics of how they work is not mysterious. Water ice condenses at certain temperatures and pressures. Clouds form. They are thick. They suppress the signal below them. We do not yet have the mathematical model to fully reproduce them, but the mechanism is understood in principle. We know what water ice is. We know what clouds are. We just didn't include them properly. The carbon chemistry of SIMP 0136 is different. The fluctuating molecular abundances imply that something is doing work on the atmospheric chemistry. Something is adding or removing energy from specific chemical reactions, producing and destroying molecules, shifting balances that should be in equilibrium. And we do not know what that something is. The leading candidates are the internal aurora and the upwelling hot plumes, but neither of these, in the forms our models describe, fully accounts for the magnitude and pattern of the variations. There is a mechanism operating in the atmosphere of this world that is not in our models. Not a mechanism we left out because it was complicated, a mechanism we have not yet identified. That is where the frontier of planetary science sits right now, not in distant galaxies billions of light-years away, in the atmosphere of a world 20 light-years from Earth, a world we have known about since 2006, a world we have been watching and studying for nearly 2 decades. And James Webb has just told us that something is happening inside it that we cannot explain. The universe is doing something right next door that we do not understand. And we have the instruments to watch it, and we have the minds to figure it out. And the figuring out is happening right now. In papers and grant applications and telescope time requests and model revisions, and late nights at the Max Planck Institute and Boston University, and laboratories around the world where scientists are looking at this data and asking themselves, with the specific intensity that only comes when you are looking at something genuinely new, what is this? What is actually happening here? That question, asked sincerely, is the most powerful force in human civilization. We have peeled back 7 layers of the atmosphere tonight, and every layer was different from what the model said it would be. We found ice clouds that ate the ammonia. We found iron clouds and silicate clouds stratified at different depths in a free-floating giant. We found hotspots generating aurora with no star to power them. We found carbon chemistry fluctuating in real time with no explanation. We found an entire population of rogue planets drifting near Earth that we are only beginning to detect. We found that the biosignature detection method depends on models that the data just invalidated. And we found, underneath all of it, a truth that is bracing if you let it land. The universe is not finished surprising us. It is not waiting for our models to be complete before it operates. It is not organized according to our simplifications. It is doing what it does, right now, 20 light-years away, in the atmosphere of a world bigger than anything in our solar system, in the dark of interstellar space where no star shines and nothing but the planet's own internal fire provides the energy for the storms. And we can see it. We can read its atmosphere. We can watch its weather. We can measure its chemistry at a resolution of 1.8 seconds per data point. We can see the aurora and the clouds and the carbon molecules shifting as it turns. That is what the James Webb Space Telescope is. It is not just a scientific instrument. It is the first time in human history that we can genuinely see the detailed reality of worlds beyond our solar system. Not infer them, not model them from indirect measurements. See them, in enough detail to know when the models are wrong. We spent decades and $10 billion building this telescope. We launched it on Christmas Day 2021 and watched it unfold, one terrifying step at a time, in the cold vacuum of space a million miles from Earth. We did all of that to see things we had never seen before. We succeeded, and what we saw broke the models. That is not a failure. That is the whole point. That is exactly what progress looks like. You are living in the moment when the best instruments we have ever built are showing us that the best understanding we had was insufficient. That is an uncomfortable place to stand. It is also the most exciting place science has been in decades. So when you look up at the sky tonight, and you are in a dark enough place to see the stars, find the southern constellation Indus if you are in the southern hemisphere. 12 light-years in that direction. There is a cold super-Jupiter wrapped in ice clouds we didn't know existed, circling a star slightly dimmer than our sun, keeping secrets about its atmosphere that we have barely begun to unlock. And 20 light-years from where you stand, in whatever direction SIMP 0136 currently sits in the sky, there is a world 13 times the mass of Jupiter drifting through the dark, generating its own aurora, cooking its own weather, reshuffling its chemistry every few hours, alone in the void, warm from its own internal heat, moving toward or away from our solar system on a path that was set in motion billions of years ago and will continue for billions of years to come. Neither of these worlds knows we are watching. Neither of them cares. But we do. And the watching is changing what we know, and the changing of what we know is the closest thing the universe has to magic. Keep watching. The next discovery is already in the data. Thank you for being here.